All right, so just a reminder, right, that our second midterm is next Monday, right? In class, same format, right, as midterm one. In terms of materials, obviously the focus, right, is going to be on exotic option. Right. You know, I mean, depending on how much we will cover today, I think we'll look at the PDs for the look back and for the Asian option. But anyway, right, I mean, the point is you gotta pay attention to the things, right, that you've been doing in the homework. In other words, right, different techniques, right, to arrive at certain quantities for exotic options, such as pricing, right, using either analytical solutions or, you know, I don't know, Monte Carlo, right, even though it's not too reliable, but we can get something there. And then, right, on top of that, relations with the Greeks, right, and how to verify the PDEs, right, you know, with the numerical differentiation and with the, let's say, an analytical formula, right, that we have. So it goes without saying, right, that you should know the, you know, analytical solution. So in other words, right, the H function. Again, right, I mean, no one asks you to memorize it, but you should kind of know where to look it up and know how to code it, right? Right, the PD, right, the Greeks, and some Monte Carlo, right? So that's the focus. All right. Any questions about this? All right. So, you know what? I feel like we didn't do the PDE in our first midterm, right? When we covered the first midterm, we did not focus on the PDE too much. So it depends, right? You know, I could go back to the Greeks of the and the PDE of the regular Black-Scholes as well, right? That's also a relevant topic. Doesn't have to be for the exotic options only. Okay. So regular Black-Scholes also can be covered, which, you know, supposedly is easier, right, than the exotic options. All right. So anyway, if there's no question, then let's return to where we were last time, right? We were discussing the reflection principle, right? Where basically, right, the picture is, suppose you have a level, right, M, and a Brownian motion, right, that does whatever it does. And the moment, right, it crosses the level M for the first time, we reflect it, right? We reflect it. So this is BT, right? And the previous one is WT, right? So BT will be WT if T is less than tau, right? Like this, right? And will be 2M minus WT, right? Which is really M minus, right? M minus WT. So that's a reflection, right? From the level M, you subtract the difference, right? If T is bigger than tau, right? So two important results, right? That we, so this is tau. Two we talked about last time. The first result is that BT itself is a Brownian motion, right? The second result is that the so-called reflection principle itself, right, which says that for, this is very important, right, for K less than M, all right, don't forget this, then the event that WT is less than K and MT is bigger than M is the same as the event BT bigger than, you can throw equality here somewhere, right? Because they're all continuous stuff. So I don't think it hurts to have it or not have it. 2M minus K, right? Okay. So again, right? So we discussed last time on why these two events are the same, right? Equivalent. And the importance, right, is the following. So let's try to remember, right? A picture here I think is super helpful in many ways. So suppose this is WT, right? This is MT, right? By the way, right? I think everyone knows by now that MT is the running max, right? I don't have to rewrite the definition of MT. Then, right, the domain of the joint, right, between WT and MT is this part right here, right? So basically this part, well, right? The reason is, right, MT is positive and MT, right, is bigger than or equal to WT, right? Now, so on the other hand, right, the domain, the area we're looking at, right, is such that, right, so here's K and here's M, right? So basically, right, we're looking at this area right here, right? The probability that W and M is in this area. Notice that there's one thing that is important for us, right? Is that this corner right here is completely inside the domain, right? Well, like I said last time, it doesn't really, it makes complete sense, right? If you want to look at, let's say, K prime, right? So for example, right, the event that instead of, right, WT less than or equal to K, MT bigger than M, you say K prime, right? Then the domain for K prime, right, is not exactly, right, a rectangle, but it involves something like this, right? Okay. Now, so that seems, first of all, I want to emphasize that K prime makes logical sense, right, in this set. But if you use that, it won't translate to, right, K prime here. Okay, we did use the fact that M is bigger than K, right? When we derive this, right? So this fact is crucial, right? Remember, if K is less than M, implies that 2K minus M, right, is bigger than, 2M minus K, right, is bigger than M, which implies that, right, the Brownian motion has been reflected, right, for BT to be bigger than M, right? Because if BT has not been reflected, then it can only be less than M, right? So in other words, T is bigger than tau, right? The Brownian motion has been reflected. So we're in this region, right? This representation. To go back. On the other hand, right, looking at the shape of the joint distribution, right, you see that. So what's the importance, right? The importance of the reflection principle, as I said. So let me just write something like this, right? Probability that WT less than or equal to K, MT bigger than or equal to M will be equal to probability, right? BT bigger than or equal to M minus K, right? And for now, let me just write something like this, right? It's 1 minus N to M minus K, right? Where we retain a notation that N of X is a probability. Oh, you know what? It's not the same, right? I have to modify a little bit. So 2M minus K divided by square root of T, right? The standard normal less than or equal to X, right? The reason, right, is because this is normal 0T, right? So I have to divide by square root of T to normalize it. Okay. But anyway, right? So this is the importance, meaning that, right, you see, you get the joint, right, distribution of WT and MT in this expression, right? So notice right here, it's very tempting, right, to differentiate with respect to K and then with respect to M, right, of this expression to get the joint density. Yes. All right. So you just differentiate this expression, which is very easy because this is the standard normal. So you differentiate this, you get to the PDF, right? The normal PDF. Except, you see, this picture tells you that if K is bigger than M, because of the shape of the region, you won't get the density at all, right? Because if you move a little bit, right, in K and move a little bit in M, you don't really get the change in the joint density because of the shape of the region. So for this reason, right, of course we would want this, right? We don't want some complicated expression. The corner of the right set, all right, being inside the region exactly allow you to get down to the density. Okay, if somehow you got this expression, which is impossible to begin with, right? It won't work here. But also this action is not true unless the corner of the set is inside the domain. Is that okay? Does that make sense or no? All right. So I hope that takes care of it, right? Now, of course, right, once you get the joint density, then you can recover, right, any kind of probability of any set you want, right, inside the region, right? Once you get the joint density, then you can recover any probability you want, right? So that's the reflection principle, right? That's the whole point, right? It allows us to derive the joint, between a Brownian motion and its running max. Any question? All right. So now, unfortunately, right, or whatever, fortunately, who knows, this expression is still not easy to use, right? To be used. So we will, so how to say this, right? This, it may not be, as you can know, right? Directly useful in option pricing yet. Because basically, have you guys, if you have taken probability, right, you know that you're given a joint density, right? Integrating out the joint density actually takes a lot of work, right? And a lot of mistakes and a lot of, I don't know, sometimes you just cannot integrate it, right? So you want to get some other, right, useful expression that comes out of this, right? So this is where the H function, right? Alpha, beta, right? KB function, right? Comes in. Okay. So let's see. You guys have worked with it for a while now. So let's see if I can do this. So it's going to be expectation, right, of e to the alpha w t plus beta mt. And then on the set that wt is equal to k, mt equal to b. Am I right? So again, right, there's no shame on not memorizing this completely, but let me check. Yeah, the only thing is this should be a T, right, instead of an S. Doesn't really matter. Okay. Okay, so how to say this, right? How you should look at it, right? You guys have been using this, right? Accepting it, right, in your homework. But what does this really mean, right? What does this function represent? Well, so first of all, right, the structure of it may be a bit strange, right? Why do you want an object like this? So this is obviously useful for auction pricing because a stock model, right, is st, right, equal to s0 e to the something, right, plus sigma wt, right? So you see that, remember, when we look at the max, right, then the max can be transferred inside and it completely, right, becomes the exponential of the running max, right? So this is why this exactly, right, this exponential right here is directly connected, right, with the, the structure, right? So that's the only reason, right? Is the stock model is an exponential of the Brownian motion. So therefore, right, exponential of the Brownian motion and the running max is knowing, right, knowing this expression is useful, okay, for option pricing. Now, in general, right, suppose you have to deal with Brownian motion and, right, this in general, is this expression useful? What do you think, right? Suppose that, beyond option pricing, suppose you just want to know these two together, is this useful? For example, right? I mean, I don't know. Suppose you want to find expectation of MT, right? Which is a reasonable question. Would this expression be useful? I mean, at least from the face of it. You want to say something, Kareem?
I was gonna say yes, because you can set like k equal to 0 or something, and then you kind of have almost like a moment generating function for e, but almost.
Right. So you have that's good, right? So you observe something, which is actually what I want to say, right? So the h function right here, the way I want to look at it, again, it may or may not be useful, is like a moment generating function for wt and mt, right? Except that, like Kareem observed, it has this thing tagged along, right? Which actually can be useful in some way and not useful in some other, right? Now, so what Kareem was suggesting, right, that is, what was the maybe? The maybe is if you can do this, suppose you do 0, right, beta, 0 and 0, right, which is exactly the moment gen function for MT, right? Agree? Oh, by the way, right, did I do this correctly? Is this correct? Is this correct?
I don't think so, because WT should still have an indicator for WT greater than K.
Correct. So what if I want this, what should I plug in? If I want this, what should I plug in here? I should plug in
Infinite?
minus infinite, right? I mean, if you plug in infinite, then actually it's 0 because, right, this is no empty, right? So minus infinite, all right? So again, right, notice that here what I'm doing is I'm trying to work out this expression. And just because something is technical doesn't mean you cannot understand it somewhat. On the other hand, right, like I said, I mean, if you don't work with something like this, like at least at some conceptual level, when you use it, right, you're bound to make mistake because you just plug in some wrong value or something like that, and you may not use it to its full potential. So, right, so what Kareem was saying is if we can do this, right, then we can, this is exactly right, the MGF of MT, and then you can use that too, right, get the expectation, right, by differentiating it once, for example, and plugging 0. But so this sounds cool and good, but where does the maybe come from? Where is the maybe? Where is the maybe come from? This is a technical part. Where is the maybe come from? Where does the maybe come from? Like again, right? Like I said, you're faced with some technical stuff. You better know, right, the limitation of your tool sets, right? What's the maybe about?
There should be a bound on beta, I think, right?
No, not really. Theta? What do you mean by theta? Beta?
No, I mean beta. So it doesn't
No,
exclude.
I'm not so sure. I'm not so sure. But I think so you're concerned about this expression, whether it is defined or not, right? That's true. I'm not sure if the running max has a moment gen function. I think it might does. It might, right? I don't think it's that bad. But then you're right, right? So there's a technicality of like whether does this exist or not, which is right. The moment gen function may not exist for all random variable, which is a good thing, right? But the maybe here I want to talk about is just a very mundane maybe. Maybe. Do we know HT alpha beta KB for all possible values of alpha beta KB? At least do we have this as readily available? By that we mean, right, the literature, the reference that you have, right? Did you take a look at the notes and pay attention to this question? So again, right, I mean, who knows, right? In reality, you don't know what kind of reference you may come up with, right, that somehow can compute this for all. But at least, like, in terms of your resources, right, which I provide you with, you know this for all values. I don't think so, right? There's only a certain combinations, right, of the values that we know of. Okay, let's take a look. You see? So here, this is the definition, but we only have, right, this expression for some special cases, right? When, for example, when beta equal to 0, right? And when and when this is minus infinity. So probably, right, this is exactly what we want. So maybe, right, this is you can use this formula, I think, right, to do this. So yes, so to answer the question, it seems okay, right? Because here, right, this formula would be working. I don't think it has any limitation on the beta and B, for example, right? So there you go, right? So this is something that, right, no one will tell you all the cases, but you want to play around with, right, to see if the tools you have, right, cover the case that you want. So right, seems okay, right? I don't know. Seems right. Notes as HT alpha beta minus infinity B, right? Formula. Well, what's the way to find out? Well, the way to find out is test it, right? So this is going to be a good midterm question. I'll let you figure it out, all right? So in other words, right, there are many ways to play around with this, to test, right? So again, the concept is very simple. You have a question, you have some candidate answer. How do you verify, yes, whether or not this kind of thing holds, right? So I'll see, right, if, well, you can try to see if this will show up on your midterm, right? So anyway, so, right, it seems like, right, this is general enough for some of the purposes, right? But it's very, very useful for option pricing because we're right there, all right? Now, so what I want to say is, right, so the point, right, the challenge is to translate the option pricing expression into, right, something that can be computed with the H function. All right. The reason though, right, and the main reason, the main difficulty, I would say, right, is the stock price is exponential of Brownian motion with drift, right? While, right, the H function itself doesn't have, right? The H function is directly Brownian motion and it's running max, no drift, right? This is not the max of the Brownian motion with drift, right? As we say that before, right? We did say that, for example, right? The max of, let's say, you know, alpha t, right, plus wt, let's say, is not the same as the max, right, of alpha t, right, plus the max of wt. All right. So we need to get rid of the drift before we can put the max, we can look at the max of our motion. So to get rid of the drift, is where you use the Gasanov's theorem, all right? So this is where knowing Gasanov's theorem precisely is required, because that Gasanov kernel, right, will be that Gasanov kernel would exactly be part of the exponential function. All right. So that's why to decide alpha and beta, right, this kind of thing, will be exactly part of it will be constructed by the Gasanov kernel. Okay. So that's more or less the main challenge when you do pricing and you want to transform it back to the H function. There's some other challenge, you know, like you have to look at the domain. But these are easier. So when you, most of the time you have to look at something like this, right? So you need to transform it to, like, you know, I don't know, MT bigger than some other number, right? Something like this, but it's kind of standard. But you got to also pay attention because, you know, there's some change of measure involved, right? Because this is Brownian motion with drift. So usually, right, it will be m hat, right? This is the running max of the Brownian motion with drift. So but that kind of transformation is pretty okay, right? The main challenge is exactly the change of measure. All right. So let's see how that's done. Okay, let's see how that's done. So our main target, right, is the up and out call. Okay. So the up and out call, right, will be, let me just do V0 because it doesn't really change anything with VT. So V0, right, is going to be E tilde, right, e to the minus RT, right, ST minus K plus, indicate a function that, MT, right, bigger, sorry, MT is less than L. All right. Okay. So that's the expression, right? Because if the running max is less than L up to time t, then that means the option is in the money, right? Sorry, it's not striked out yet, so you get paid this much. Okay. So, right. So exactly, this, right? Oh, sorry, it's not MT. God, right? I made a mistake already. This is not the right notation. It's the max, right? So yeah, that's exactly the second challenge. The max of the ST, right? It's not M. M is reserved for Brownian motion, right? The max of the T is less than L, right? So, yep. Okay. All right. So, for some technical reason, right? More or less has to do with the way the H function is constructed, right? It's bigger, right? Bigger. So even though, right, strikeouts like this, right, we would like to have it in the direction of bigger, right? We want to have it in the direction of bigger, right? So you already know what, right, is going on. We just flip the to indicate a function, right? Like this, okay? So again, right, this step is purely technical. It's just, right, it's exactly in the spirit of, right, transform the option pricing into the H function, right? And so we want the bigger just because of that, right? And again, your homework, right, you're already quite familiar with this kind of combination. Okay, so now we want to work with this event first, right, to see what happens. And I kind of alluded to that, right, many times now. So the max, right, will be S0 e to the, right, the max of, right, R minus 1/2 sigma square T, right, plus sigma W tilde T, right, like that. This is the max of all T. Okay. So now, right, notice there's something here. So there's still this sigma, all right? There's still this sigma. So this sigma, right, we want to hit the max on the Brownian motion itself. This sigma has to come out, okay? This sigma has to come out. Otherwise, right, this is not Brownian motion with drift. It's Brownian motion scale and then drift, right? Gussanov doesn't work at this level. Gussanov works with Brownian motion with drift. All right, so let me tell you, right, recall, right, Gussanov says that, right, if we use the change of measure kernel, which is, right, e to the minus, right, 1/2 theta squared T, right, minus theta WT, like this, okay? And, right, WT, let's say, is a P Brownian motion, all right? And then you define E tilde, right, of X to be E of ZT times X, right? Then W tilde T, which is WT plus theta times T, is a P tilde Brownian motion. All right. Now again, right, I do admit it's a mouthful. It's a lot to take in, right? If it's the first or actually the second time you see it. I just want you to appreciate the importance and why we need to memorize this or internalize this. It's like this, right? It's just like the direction is super important. That's all, right? Before, it's not so much important because you know that you know where you want to get to a risk neutral probability, right? You will not do it, you will not get wrong. Here, right, you will completely get wrong if, for example, right, instead of a minus here, you remember it's a plus. You will completely get wrong if you put the ZT on this side rather than ZT on this side, right? Also, you'll get wrong if you don't remember if it's a plus or a minus. Why, right? Because all of these, like I said, will enter into the function, right? If you mess up one coefficient, your whole function will be messed up, right? And again, I think the homework of this week, if anything, it teaches you anything, right? One wrong coefficient or one wrong something, right? The PD will not be verified, okay? So, well, you know, because things have to be very precise. So therefore, right, we need to make sure everything is lined up correctly. And in relevance of this, what I'm trying to say is, right, this is the structure, right? We want to basically transform this guy somehow into a new Brown motion, but right now it cannot be done because there's still the sigma. So the next step is to factor out the sigma, okay? So I'll skip, right, these two parts. And the sigma, right, because it's positive, right, it will just be sigma times the max. Right? So now, right, this is exactly in this structure, and we'll give this a name, right? What do we call this? You guys should know it by now. What do we call this in the notes?
That should be theta, right?
Yeah, here is theta, but if you have done the homework, you know what the note refer to it as, right? I just want to be consistent. Exactly, that's the alpha, right, in the notes. Right? That's why that's, remember, right, there was an alpha right here. You see, alpha. And in this glorious formula that I'm sure, wait, hold on, you looked at several times, right? Right here, this formula, right? The WTX, the alpha, right? This alpha, right, is this number right here. And the reason was exactly because of the Gaussian. You understand? So, I mean, nothing wrong with what Kareem's suggesting, right? We call it theta. If, you know, we follow the Gaussian's notation, right? That's probably natural, but here we'll call it alpha, right? To get in line with the note, right? And the notation you guys have been using so far. So this is sigma. All right, where alpha is r sigma squared over sigma. All right, so now you know where sigma, where alpha comes from. Okay, so, right, that suggests that what is our change of measure kernel? Change of measure kernel would be e to the minus 1/2 alpha squared, right? T plus alpha w tilde t, right? Because we want to transform from alpha, from w tilde to something else. Sorry, I made a mistake myself, right? It's a minus. All right. And let's write it down, right? Let's write it down very carefully, all right? Because again, like I said, there's something that you may not expect. So this, right? So the change of measure will be E hat, right? Of x will be E tilde of x times ZT. Agree? And if we perform this change of measure, then W hat of t, which is W tilde t plus alpha t, right? This glorious object that we are looking at here is a E hat round motion, or P hat, right, if you want. All right. Okay, so far. So now, right, let's just focus on this expression, right? This is exactly the WTX function that we were looking at, right? Where, x is really S0, right? T is 0, right? So let's focus on this function. This expression. Right? So what would this be? This will be E tilde of, right, ST, right, exactly, it's just S0 E to the R minus 1/2 sigma squared T, right, plus sigma WT, which is sigma times W hat T. Agree? And then E decay function of the max, right, which we always write as S0 E to the M hat T, right, bigger than or equal to now. Sorry, right, there's a minus K plus. Okay, so far? Any question about this? Any mistake you spot? Just tell me. Okay, so right, obviously then we want to get rid of the plus, right? So we want to do something like this. And then we just throw in another indicator function, right? That W hat T is bigger than log, right, of K over S0 divided by sigma, right? And the same with the other indicator function, right? I don't know, M hat T log of, sorry, there's a sigma here, right? You guys should have spotted that. 1 over sigma L over S0, right? This is, again, right? These expressions should be familiar, right? You guys have used that. Thank you for teammate, right? I was about to ask that, but be patient. You are saying something there, good. But, right, so for teammate was telling me, wait, I made a mistake, it should be E hat. Well, so let me ask this, right? So can we use the H function now? Or, yeah, for teammate was saying that the second E should be under the new measure. How does that work? These are kind of similar. Yeah, these are questions on the same topic, right? So for teammate seems to imply that I'm making a mistake. Is that right? That's what Fatima was saying. Should be E hat. I claim that, well, I don't know. I just want to use the H function. So what do you think, right? Any mistake that I've done so far, or what to do next? Again, right, it's important that you spot whether I made a mistake or not, or what kind of nature, right? So that you understand what's going on. What do you think? Anyone? All right, so first of all, right, I was just purely, you understand where it's coming from, right? This is V0, this is risk neutral pricing. I converted to a bigger than because, right, and throw in the black show because, I want to use the H function, right? Which you see I was successful because, right, that's exactly the bigger than that I was using, right? And so then I just, of course, this everyone knows what it is. So I just focus on this expression, right, with E tilde. And I was purely, right, rewriting things using this definition, right? This is what, do you agree? This is W hat. So, I mean, that's W hat, basically W with the right drift, right, with the right drift. So there you go. So did I make a mistake? Maybe yes, maybe no. Can we use the H function now? Is this too hard?
Did we not multiply by ZT to get exponential of H of the hat measure?
Right. So Kareem actually is seeing something going on, right? So you're almost there, Kareem, right? So first of all, the answer here is no. What's the reason? Because what? W hat is not a E tilde prime motion or P tilde prime motion, right? So do pay attention, right? And this might be confusing to you guys if you don't master change of measure very well. Symbolically, I'm not making any mistake. Okay, I'm subbing in, instead of this expression, I sub in the W hat, right? And I define W hat like this. So symbolically, I'm not making any mistake at all, right? I'm just subbing in. This is just pure algebra. The mistake will come in, if any, is where I will try to identify this as a prime motion while I still have this. And this is maybe what Fatima is calling out for. All right. But so far, notice that this is really E tilde. I have not done anything, right? I'm just symbolically changing the inside, which is purely fine, right? I will make a mistake if somehow I claim that this is a prime motion and this is a running maximum prime motion, right? For the purpose of using the H function. I'm not doing that, right? Or no. And this is where Kareem, right, exactly recognized that there's a ZT lurking around somewhere, right? Okay, to convert to E hat. So tell me, right, how do we get the E hat to show up? Can I just write E hat like this? Again, I'm not trying to imply that Fatima was suggesting this, right? But if I somehow magically convert it to E hat like this, is this correct? So Fatima was saying this. So, right, by same, I mean this, right? I'm too lazy to write this, all right? So like this, so is that correct? No, right. So what's the right one? One over ZT. Okay. What's the reason? The reason is ZT, right, as the structure is going forward, is going from E tilde to E hat, all right? This is exactly why I was telling you that you got to pay attention, right, to the sum of. Again, I know, right, that it's hard to memorize all of these, but I want to convince you of why it's important. Yeah, that's fine, right? You're talking about something else. Basically, you can do forward, backward, which is true. Sometimes you cannot do that, but here is fine, right? You can go forward, backward. I mean, that detail, let's just accept it. What I want to emphasize is, right, the formula like this is going this direction. Now we want to stay at E hat, right? So we want to convert almost like E hat back to E tilde. That's why it's 1 over ZT. Okay. So now, right, with the ZT in, which is the alpha expression, right, that concludes, right, the details of what the H function should be, right? So there are two H functions, right? So let's try to see if, so can anyone, so let's write down again, right? So H, right, of T, right, alpha, beta, KB, right, is equal to expectation of e to alpha WT, beta MT, indicator function that WT bigger or equal to K, MT bigger or equal to B. Right? So can anyone tell me, right, that, by the way, right, so ZT is e to the 1/2, right, minus 1/2 alpha squared T, alpha W tilde T, right? Oh, by the way, right? So this is ZT, right? And this is ZT. So ZT inverse will be a plus here, right? But is there any work that we still need to do to convert this expression to the H? You notice, right? Any work? So the same, right? Same is exactly this expression. Any extra work do we need to do before we can start from here and use the H function? I hope you're not overwhelmed with the symbol, but this is W tilde, all right? It's not WH, W hat, okay? Because we're under E hat, right? So we need to transform this one more time to W hat, right? Which is what? How do you convert it to W hat? Agree? So, right, again, probably one of the most technical thing that you have to do in this course. But I want to convince you of why, right? All these steps are necessary. They're not just easy work, right? You got to line things up correctly, even though, right, the H function is already cooked up for you, right? So okay. So anyone cares to tell me, right? So forget the e to minus RT, right? That's the first part. So the above expression, right, is e to minus RT, let's say, right? What's the first H function? What's the first H function? What's the value here for little t? Oh, it should be, right, e to the minus RT. You also pull this out, right? So e to minus R minus 1/2 sigma square, right? T. Like this. All right. So that takes care of this part and this part, right? So what's the H function for the first part? What's the coefficient here? Big T, right? What's the alpha? What's the alpha? Alpha will be alpha plus sigma, right? Because these are the two exponential, right? That comes up. What's the beta? Correct, right? There's no M to show up. What about the K? K is this. B is this. Correct. Right? So that's the first H. What about the second H function? Oh, hold on, right? I think we're missing an S0, right? The S0 is coming out of the first one, so there's an S0. Like this, right? What about the second one? It's a K, right? H, T. What's the alpha and sigma? What's the alpha and beta? What's alpha here? Alpha, just alpha, right? Because it's the alpha of the, yep, just the alpha of the, this, correct? And then the two others are the same. Okay. So I think now if you want to be fancy, right, you can write this as e to the minus sigma alpha t or something, right? Because that's how we define alpha, but I don't know. All right. So I was not looking at the notes when I wrote this down, right? I was just purely forming math. Well, let's check the notes to see that I got it right. There you go, right? Voila. Yeah, of course. I was deriving that, right? This is exactly that. Yeah, right here. Okay. Cool. At least Shinan is enjoying this derivation. Any question? Sure. So you have to remember what the beta, right, is in this h function. So the h function, right? Yeah, I write down somewhere here. Yeah, the h function, right, is like the moment gen function, with the beta being the coefficient standing in front of the running max. So if the running max is not present in the expression, then that means beta is 0. Yeah. So, right, if you look at the expression above, right, even including the change of measure kernel, which we need to, the MT does not show up anywhere, right? Because this is like the barrier option, right? If it's the look back option, then the MT will show up. right, on top of the exponential. But because the payoff, right, purely depends on the prime motion, there's no MT on the top. So that's why beta is 0 on both expression. Okay. Any other question? So, all right, to recap, right? And this recap is true for, exotic options in general. Possibly not Asian. Because the Asian option, right, doesn't depend on the max. So this doesn't work with it in terms of analytical formula. So there are two things, right? So you always have this kind of thing. So this formula, this pricing formula is always true, right? For any kind of option, as long as it's not American. Right? So true for all non-American. Right? On the other hand, right? So this is not very useful in ourselves unless you want to do Monte Carlo. So if you want to do a PD approach, right? The PD approach. So this tells you something about the martingale structure already, right? This tells you that the discounted, right? The discounted option price is a martingale. That's always true. But the challenge, right, is because the PD, remember, right? PD is a static object, right? PD is a static object. So your goal is to establish that VT, right, which is a stochastic process itself, is a function of T, the current stock price, and possibly something else if the option is path dependent. All right. It's very simple, right? Just think about it. Again, right? Remember that VTX, whatever, right? Or let me say this is not goal, but challenge. All right. All right. So basically, right, what you're trying to say is if you have the information about the current stock price, you can decide what the current option price is. But that cannot be true if the option is path dependent. Agree? I mean, if you don't have some extra information. All right. For example, right, just think of the barrier option, right? Just think of the barrier option. Suppose here's L, right? You start at somewhere here. What's that synonym? So, right, so suppose the stock, right, does something like this. And, right, so if at this point T, right, you know the current stock price, well, what can you do? If that's the only thing you know, then you probably can decide, right, from here to the future, whether the option will be above the barrier again or whatever. You also can decide what ST minus K is. But what you cannot decide with only ST is whether in the past the path has ever crossed T or not. Therefore, right, the relation between option price and the simple BTST doesn't hold for any general exotic option. Okay. So you know, right, the story is, right, with the exotic option, what we say is VT is VTST as long as you have not hit the barrier, right? So there is this, extra part, right? This is exactly the part that captures path-dependent information. But once you have that, right? Once you have that, then you can just go ahead. Once you satisfy this challenge, then eta minus RTVT is a martingale, means eta minus RT. These guys is a martingale, right? So by the way, let me say this, right? Because we know for some reason, right? So this is the up and out. So you could have eta minus RT VT, which is eta minus RT, right? VTST, as long as you are below tau, right? Is a martingale, right? So once you decide what the representation is, where the representation holds, then you can apply the Martingale principle on that representation itself. And from there, you can apply eta, right? And set dt equal to 0 and get your PD. All right. So that's the main challenge of PD for exotic option. That you need to establish this relation, right? That somehow captures a path-dependent part. That somehow captures a path-dependent part, okay? But once you do that, then you can use the Martingale principle. Of course, so let's remind you that for the up and out call, right? The PD is minus RV plus V sub T plus V sub X RX plus 1/2 V sub XX, right? Sigma square X squared is equal to 0. Now, why is this true? This is true because the representation is basically a Black-Scholes representation. Therefore, right, the apply eta and set dt equal to 0 doesn't change anything, right? Doesn't change anything, except, right, this part right here will influence how the PD behaves in its domain, right? In other words, this is only true if you stay below the barrier. And, right, if you hit the barrier, you will be 0, right? So these parts are very peculiar to the knockout option. And that's actually, right, this captures this part a little bit. Yet, right, like I emphasize again and again, even if you solve this PDE completely, you still cannot recover the option value unless you have this information. Okay, this information is not part of the PD, right? This information is read independently. Okay, like this picture, right? At this point, from the PD point of view, well, it has a value, right? In other words, right, you can end up here via many, many paths. You can end up here with a path that has crossed the option beforehand, and you can end up here with a path that never crossed the option, crossed the barrier. Okay, right? From the PD point of view, if you only know this much, you can't tell a difference. You can't tell the difference between these two paths, right? So the option, right, is determined beyond, right, the current stock price with this past behavior, right, with this past memory, and you have to attach it to the PD solution. Okay. With the analytical formula, this is only for, right, look back in Asian. Sorry, look back in barrier. Then you try to convert, right, the pricing formula to the H function, right? That's all. Now, let's try to, so what I'm trying to say that that's with the agent option, right? Doesn't have analytical formula in general. All right, so let's try to understand why this is true, right? So for example, let's say that Vt is 1 over t, right? The integral st dt minus k plus, right? Like this. So let's look at V0, right? V0 is the is e tilde, right? E to the minus RT et, right? Like that. So that's always true. But what does it take to compute this expression, right? Well, it takes to compute this expression at least, right? So let's say this, right? So let's take the e to the minus RT out. So that will be, right? Let's say 1 over t integral, right? St dt minus k, right? Let's say this. And let's say indicate a function, right? That this happened, right? So in other words, right, to handle V0, you better know how and when this happens, right? But if you look at the event, right, all you can say is, okay, like this. But that means, right, that this special, right, function, let's say it, right, is the integral from 0 to t of s of u du, right, is a stochastic process. Okay. So unlike the running max, this guy is very nice, right? It's very smooth, it's differentiable, etc. Or not very smooth, it's differentiable at least, right? But we don't know its distribution. All right. So let's just tell you something here in case you wonder, right? So this is the integral of the stock, all right? I mean, so maybe someone has done something on like this recently, I don't know, but at least 5 years ago, I don't think anyone has done anything like this. And I don't see how they can do it in the future, at least. But so the analogy of it is something like this, right? Let's say this, right? Let's say this function, right? Let's say I have IW, right? So this is the area under the curve, right? Or above the curve, whatever, of the Brownian motion. I don't think this one has no distribution. All right. Unlike the running max again. I put a question mark here in the sense that, okay, maybe I'm wrong. Maybe someone has somewhere computed the known distribution of this. But even if that is true, right? Let's say even if that is true, it may not translate to this directly. Why? Because the integral will be the integral of e to the r minus 1/2 sigma square t plus, right, sigma wt dt. Sorry, right, u du. So in other words, I guess maybe I'm making a dramatic thing out of this, but basically someone has to compute something like this. Right, the distribution. In order for us to have a shot at deriving the analytical formula for agent option. And I don't think, right, this is no. All right. So that's the reason why we don't have formula for agent option in general. Okay. Which is surprising because you, like I said, again, you may think that the integral is a nicer object, but it's a nicer object in terms of calculus, right? Notice, so it makes, I hope it makes you appreciate like the trick, right, of the reflection principle more, right? This might seem like a weird thing to begin with, but somehow it works very nicely with the max, right? With the integral, right, it does what it does, but basically there's no, I don't know, rhyme or reason to how the integral moves. So I think, yeah, that's not a known result. Okay, so the next thing I want to say is this, right? Very quickly, and then we'll continue, right, next week on Thursday, is, right, so I said the challenge. The challenge is to establish, right, something like this for V, right, the value of the option. So for the Asian option, right, what do you think? For the Asian option, let's just, take whatever it is here, right? Let's say this. So what do you think VT is equal to in terms of deterministic representation? What should go in here? So if I have a deterministic relation, right, between a function and the option value, what kind of information do I need to be able to do that? So in other words, right, at time little t, what information do I need to completely nail down the option value for agent option?
The whole path up to time t.
Yes and no, right? If you need the whole path, then that's hopeless, because that's true for any option. But notice, right, path is not a PD object. Agree? Because path is an infinite dimensional object, right? You're right, but it just cannot work with PD. By the way, this is funny because this is exactly what my advisor was working on when I was doing PhD, and he got famous for it. Basically, somehow making sense out of this structure, right? Because of course there are more complicated things out there, but the word path in here cannot just work with PD, right? Because you know what I mean, Kareem, right? Because a PD is a two-dimensional object, three-dimensional objects, whatever, right? You cannot just stick a path in here because path is an infinite dimensional object.
Yeah, I see.
Say again?
No, I said I see.
Yeah, okay.
Thank you.
Sure, but the fact that it's agent option, right, means that you don't need the whole path. What do you need? You need the current stock, and you need the integral so far. All right. Think about it. Why is this enough? The reason. No, that's the path for teammate, right? That's what Kareem was saying. That's the path. No, you don't need the whole path. The point is you only need these two objects, right? This is not the whole path. This is much less than the whole path. Right? Okay. So the reason is this, right? Basically, I claim that. So we'll write out this later, right? Claim with ST and the integral, I will know I mean, not decide, but yeah, it's almost, I can determine. Does that make sense? Because, right, that's all it takes, because that's what agent option is, right? Agent option depends on this guy, yes, in one form or another. So if I know these two pieces, I will know this. Now, what might be strange to you is why do I need this, right? Isn't this enough? In the way, right? In the sense like this, right? So you see, it's very natural, right? This is this. So that's that piece, right? So this is the past plus the future, right? Okay. So the past, right, exactly is captured with this because that's what I need. What are the future? For the future, right, notice that the future is the present like that, right? And all these are generated in the future, right? Maybe you need the current random motion, but that's implied, right, by ST. You understand? So, right, to generate a future integral, I do need to know where I am at the present in terms of the stock price, but no more than that, right? All whatever else is a future value. So if I know the current value of the integral plus the current stock price, I can generate the whole future path. Got it? So therefore, right, the PD here for the Asian option depends on 1, 2, 3 pieces, right? These are the 2 standard pieces. The last one is some extra piece. That's the path dependent piece. Okay, so I realize I kept you beyond time. So let's stop here and we'll pick up next Thursday.
Thank you, Professor.
Yep. Sure, thank you.